In this video, I will show you some examples for determining point groups of molecules. Let us first consider a simple molecule like this, CHClFi. This is nothing but a methane molecule in which the 3 hydrogen atoms have been replaced by 3 different halogen atoms. Structure of this molecule is tetrahedral and it is convenient to draw with the help of a cube. We know that a tetrahedron can be inserted in a cube like this. Draw a cube first and then take the alternate angles, alternate vertices. The carbon atom is situated here, hydrogen atom is here, chlorine is here. This is taken, then this is omitted, and this is taken, this is chlorine, this is omitted, this is, say, fluorine with a different notation, and this is iodine having a different notation. 4 different groups, and these are the bonds with carbon. This is the structure of this molecule. We note here that there is no axis of symmetry. There is no axis of symmetry, rotational axis, and also there is no plane of symmetry. In fact, this structure has only its own identity and no other symmetry element. Therefore, the point group is C1, according to the scheme I discussed earlier. Next, let us consider CH2ClF. I replace iodine by another hydrogen. The structure can be obtained similarly by drawing a cube. This is also a tetrahedral molecule. It is derived from methane. The carbon atom is at the center of the cube. The 2 hydrogen atoms, one is here and one is here. Chlorine and fluorine. Chlorine is here. Chlorine and fluorine is here. So, here we see that there is no axis of symmetry. If you consider a line like this, passing through the center of the top and through the body center, that axis will not act as a twofold axis. If you rotate the cube about that axis through an angle of 180, this hydrogen will go there and this will come here, but these 2 atoms are different. Therefore, that line does not act as an axis of symmetry. It has no axis of symmetry, but you can use this plane. You can use this plane. Cutting the cube into 2 equal halves. One half will contain hydrogen on this side, the other half will contain hydrogen on that side, and these 2 atoms will be cut into 2 pieces, one half on that side, the other half on that side, and thus one half of the cube is a mirror image of the other half if this plane acts as a mirror plane. So it is a plane of symmetry. The object has its own identity E and a plane of symmetry like this. there is no other symmetry element present. Therefore, the point group is CS. Here point group is C1 and the point group here is CS. Now we replace fluorine by chlorine. We take dichloromethane. CH2Cl2. In the same manner, we draw a cube. Carbon is here. 2 hydrogen atoms are at these positions and 2 chlorine atoms are at these 2 positions. This is the structure of dichloromethane molecule. Here we find that a line like this passing through the centers of the opposite faces and through the center of the cube, this line acts as a two-fold axis of rotation. If you rotate the cube about this line through an angle of 180, this hydrogen will go there and this hydrogen will come here. Similarly, these 2 chlorine atoms will exchange places, producing an equivalent configuration. Therefore, this C2 axis exists. Next question is, are there 2 such C2 axes perpendicular to this one? Are there 2 more C2 axes perpendicular to this C2? No, there is no other C2 axis. Therefore, it is of C type, not of D type. Next question is there any plane of symmetry perpendicular to this C2 axis? Perpendicular to this C2 axis will be a plane like this, cutting the object, cutting the cube into two halves. But the 2 halves are different. This half contains hydrogen and this half contains chlorine. Therefore sigma H plane does not exist. Next question is whether sigma V plane exists. Yes. If we take this plane, it will cut the object into 2 equal halves. Therefore, this is a plane of symmetry. And again, we can take these 2 diagonals, this one and this one. Taking these 2 diagonals and these 2 edges, we can find another plane of symmetry. Cutting the object into 2 equal halves. These 2 are of sigma V type, vertical type, because they contain this C2 axis. In fact, these 2 planes, this one and this one, intersect on this line. They intersect on the C2 line. Therefore, they are vertical planes. So, this object has an identity, then a C2 axis, and then 2 sigma V planes. No sigma H. So, the point group is C2V. Take another example. Consider phosphorus pentafluoride, PF5. It has a trigonal bipyramidal structure like this. Here there is phosphorus, F. The PF bonds, these are the equatorial bonds, and this is axial bond. We find that this axis acts as a C3 axis. If you rotate this molecule about this axis, these fluorine atoms will exchange places. So a C3 axis is present. Next question is, are there 3 C2 axes perpendicular to this C3? Yes. This line along the PF bond acts as a C2 axis. You can turn the molecule through an angle of 180 about this axis. This fluorine will go up and that will come down, and this front face of the triangle will be turned into the back face. So this is a C2 axis. Similarly, there are 2 more C2 axes, this one and this one. There are 3 C2 axes. So there is one C3 identity, then C3 axis, then 3 C2 axes perpendicular to C3. So it is of D type. Then our question is whether sigma H plane exists. Yes, if you consider this triangular plane, it is a plane of symmetry. This plane is a plane of symmetry and it is perpendicular to this C3 axis. Therefore, it is a sigma H plane. A sigma H plane exists. So, our point group is D3H. Note here that this object has vertical planes also. This is a plane of symmetry, sigma. It is not sigma H, it is of sigma V type, vertical type. I am spelling it out because sigma V types can again be classified into sigma V and sigma D. Anyway, it is a plane of symmetry containing the principal axis. So, if you try to find out sigma V first, then sigma H, then you will arrive at an incorrect result. You have to find out sigma H first, then there may exist sigma V. That will be a consequence of existence of sigma H. This will be shown in our further discussions. Next, let us consider PF4Cl. Replace one fluorine by chlorine. The shape is again trigonal bipyramidal. Only we are replacing fluorine by chlorine. These are all fluorine atoms. And this is phosphorus. What is the point group now? Here also, this line acts as a C3 axis because there are fluorine atoms which will exchange places when this C3 operation rotation is carried out. But this line does not act as a C2 axis, because if we turn it through 180, chlorine will go up and fluorine will come down. The configuration will not be equivalent. So no C2 axis exists. And then sigma H. Is there any? Does this plane act as a sigma H plane? No. This plane also does not act as a sigma H plane, because on one side there is fluorine, on the other side there is chlorine. However, these planes, one plane is like this, containing this PF bond and this axis. You can imagine a plane of symmetry that will cut the object into 2 equal halves. Because chlorine is contained here, it will be cut into 2 equal pieces. One piece will be the mirror image of the other if this plane acts as a mirror. So this is a sigma V plane. Once you find one sigma V plane, you are sure that there will be 3 sigma V planes. If Cn is present and one sigma V is found out, then there must be n sigma v planes. Here, using this PF bond, you have found one sigma v plane. Similarly, using this PF bond, you will find another sigma v plane, and using this one. So we have one C3 axis, first identity, then one C3 axis, no C2 perpendicular to this, and three sigma v planes. So the point group here is C3V. So I consider more complicated examples in the next video. Let me thank you for your patience, and thank you for watching this video.